Hello APC Mechanics students in Unit 3 Work Energy and Power, Class 6, 3.1 Forces and Potential Energy, Part 3. Then Section 1 recap. In this video we're gonna solve some exercises. Before doing so, we will do a recap on what we have discussed so far in this unit. Let's recap the main points related to the previous classes. A conservative force can be derived from a potential using calculus by. The work done by a conservative force is path independent and depends on the initial and the final position of the system. And it can be calculated using the negative variation of the potential energy. A conservative force is always directed toward least potential equilibrium position, and it converts energy from one form to another without any loss. A linear spring Hawking spring stores elastic potential energy given by half kx squared. Near the surface of a planet, of a system consisting of an object and a planet, this system admits gravitational potential energy given by mgh, where the PE level is choice-based. If the center of mass of the object lies above the PE level, this means that UG is positive. If it's below, it's negative. And if it's at the PE level, that would be 0. Two massive objects M1, M2 separated by distance r admits gravitational potential energy given by minus gmm over r, where m and m are the masses of the two objects, and in this case they are given by m1 and m2, so here I should have placed m1 and m2. Now exercise 1, the variable x represents the position of a particle in a two-particle system. Particle B remains at rest. The graph above shows the potential energy U of the system as a function of x. The x component of the force on a particle A, when is it at x 0.15 meters, is most nearly. So now we are familiar with some tricks related to graphical reading. Here in this case we have U versus X. And remember that if we're talking about a force which is derived from a potential, which means a conservative force, it can be determined using Fx is minus du by dx. Du by dx has an interpretation which is a graphical interpretation, which is the slope of the tangent at a particular point x. Now we are interested in determining the component of the force at 0.15. Then we will plot the tangent at 0.15, which is here at this point. Now after plotting the tangent, now we need to determine the slope of the tangent, and this is done by choosing two particular points. I will choose this point and this point as well. So the slope in this case would be given by, the points are 0 and 2. So let me write 0 and 2 joules, and the other point would be 0.1 meters and 0 joules. Now we're ready to calculate the slope, which is given by 0 minus 2 over 0.1 minus 0, that would be minus 20, and this would represent a force which is in newtons. Now this is the slope, so the slope is given by minus 20 newtons. Now we need to add an additional minus sign because it's negative of the derivative. Then the correct answer in this case would be E. Now exercise 2, an object is pushed into a non-ideal spring compressing the spring. The magnitude of the force F the spring exerts on the object as function of the compression axis shown in the graph. Here in the graph we have F versus X. So as we compress the spring, we are plotting the magnitude F. So pay attention that this is the magnitude. This is very important. Which of the following graphs best shows the potential energy of the object spring system as function of X? Now you can approach the problem in two ways. Either you consider that you have this graph and you try to determine the U versus X graph, or we can do it the other way around, is that try from the solution, check which one would correspond to the given F versus X graph. Now we need to refer to the formula which is given by Fx is minus du by dx. So in this case what we're doing is the following. We will refer to the potential graph and try to interpret the slope in order to have the Fx graph. First of all, if you consider the function f, it's a variable function. which means that the slope should be variable. And directly we can eliminate A and we can eliminate B, because for the graphs of A and B, the shape of the curve is a straight line, which means if we consider the derivative, which is the slope, it will be constant. However, this doesn't agree with the given curve of f, because f is increasing. It's not a constant. So if you consider A and B, we would expect that the graph of f would be something like that, a constant. Now we're left with three choices, C, D, and E. Now the magnitude of f increases, which means the magnitude of the slope should be increasing. Now let me start, for example, with D. Then let's do the slope for this graph. The tangent here is something like that, and it's something like that, which means the slope is decreasing. For this reason, we can directly eliminate D. Now what about E? Okay, the slope is increasing. Why? Because let me draw different tangents. In order to understand more what's happening here, let me give some values. Let me say this is -5, this is -4, and that would be, for example, -2, and that would be 0. So it is indeed increasing, but in magnitude. We're interested in magnitude. In magnitude, it's decreasing. So let me write down the slope is increasing, but the magnitude decreases because we're moving from 5 to 4 to 2 to 0. For this reason, we're left only with C, and indeed, if you interpret C, the slope here in this case is positive all the way up. So we can say this is 2, 3, 4, 5. Indeed, the slope of the U versus X graph is increasing, which makes C to be the correct answer. Now, exercise 3, figure 1 shows a block that slides up a rough incline, momentarily comes to rest near the top of the incline, and then slides back down the incline. Figure 2 shows a free body diagram of the block as it moves up the incline, where N is the normal force, F is friction, W is the pull of gravity. Figure 3 shows the FBD for the block as it moves down the incline. Based on these figures, which of the following is the correct statement? Since friction changes direction as the block motion changes direction, friction is a conservative force. We know that friction is not a conservative force. Since friction is always against the motion of the block, the total work done by friction is 0. No, the work done by friction is always negative. Since the normal force is always perpendicular to the motion, the normal force is a conservative force. Now we know that. The normal push is not a conservative force. Since the component of gravity is always directed toward the original position of the block, gravity is a conservative force. Yes, this is correct. Why? Because we know that for a conservative force, the direction of the force is always toward the least potential, and in this case it is down. And what about part E? They're saying that the gravity is a non-conservative force. This is wrong. A particle is moving along the x-axis under the influence of the spring force Fx. The potential energy of the particle as function of the position x is given by the equation, where beta is half joules per meter to the power 4. The magnitude of Fx when the particle is at position 0.1 meters is most nearly. We need to find the magnitude. Then this can be done using calculus, because we know that Fx would be minus du by dx, which is minus d by dx. This can be utilized as an operator of beta x power 4. Now beta is a constant, it will be saved due to the multiplication, it will be dragged out. And this is a power function, we drop the power and decrease the power by 1. And that would be beta is given by half 4, and at a particular position given by 0.1. Now plugging that on the calculator, that would give us minus 2 times 10 to the power 3. The force F is in newtons. And the correct answer as a magnitude would be C. And here let me mention a side remark. Why beta is given by a dimension of joules per meter to the power 4? This can be done by referring to the dimensional analysis, because we know that U is given by beta x to the power 4, and we're interested in determining the unit of beta. So beta would be given by U divided by x power 4. U is energy in joules, and x is meters. So that would be meter to the power 4. Then the unit of beta has been fixed anyway, such that U would be joules. Now exercise 5, a nonlinear spring is used to launch a toy car. The spring is nonlinear. Once the spring is nonlinear, we cannot use that the elastic potential energy of the spring is given by half kx squared, because this expression only works whenever the spring is linear or ideal or a Hawkian spring. The car is pushed against the spring, compressing the spring 2.5 centimeters. The force the spring exerts on the car is given by the equation F is minus kx squared, where k is 5,000 Newton per meter square. Now we're used to the fact that k is given by Newton per meter. Because F is quadratic, then k would be given by Newton per meter square. If F is linear, then k would be given by Newton per meter. The potential energy stored in the spring when the car is pushed against is more nearly, so we're talking about the potential energy, which means that this force is a conservative force, and the potential energy can be determined from the equality given by the change of the potential energy is equal to the minus the work done by the conservative force, and the work done by the conservative force can be expressed as an integral of the dot product between the force and the displacement from an initial position to a final position. Now let's replace the expressions that we have. The force is given by minus kx squared, minus would give us plus, so that would be kx squared dx. Don't worry much about the dot product because these forces are either parallel or anti-parallel, and luckily all of our choices are given to be positive values, so no need to worry about the minus sign. Now here they're telling us the car is pushed against the spring, compressing the spring by 2.5 centimeters, which means initially we started from the equilibrium, and because we're compressing, so we're going to 2.5 centimeters. Notice that this should be converted into meters, which is the SI, and this is given by 0.025, and that would be here minus 0.025 because we're compressing. Now this is a quadratic, the integral would be cubic. K is a constant, can be dragged out, that would be x cubed over 3. Now this expression would be computed between two different values given by 0 and minus 0.025. Now k over 3 is a constant, can be dragged out. And now we can compute x cubed between these two values, and that would be minus 0.025 to the power of 3 minus 0 to the power of 3. And the value of k is given by 5,000 divided by 3. This is 0, that would be multiplied by minus 0.025 to the power of 3. Now plugging that on the calculator, we're gonna have a value of minus 0.026 joules, and because our answers are positive, we're gonna go for A. And also let me do a dimensional analysis for the unit of k. F is given by k x squared. If we're interested in the unit of k, k would be given by F divided by x squared, which is Newton per meter square. A particle that is considered to move along the x-axis is acted upon by a conservative force F that varies according to the function minus k over x cubed, where k is a positive constant with the units of Newton per meter cube. So now we know that k, the unit of k, has been fixed such that F would be in newtons. Which of the following is the correct expression for the change in the potential energy as the particle moves from x1 to x2? And this can be done using the equality. The change in the potential energy for a conservative force is given by minus the work done by the conservative force, and the work done by the conservative force can be expressed as an integral from initial position to a final position of the dot product F dot dx. We have the expression of F, that would be minus, with minus that would be plus. K is a constant, will be dragged out, 1 over x cubed dx from an initial position given by x1 to a final position given by x2. And notice that here in the choices we're interested in the expression and not a numerical value, so we need to pay attention to the minus sign. Now this can be integrated by utilizing that it is a power function x to the power minus 3. Then the integral of x to the power minus 3 dx, we don't forget the dx, we add the power by 1 and we divide by the final power, and that would be x to the power minus 2 divided by minus 2, which is basically 1 over minus 2x squared. Then the result would be given by k into minus 1 over 2x squared computed between two values x1 and x2. Now k minus and 2 can be dragged as a factor, and we're computing the expression 1 over x squared between x2 and x1. That would be 1 over x2 squared minus 1 over x squared Now, once you reach this answer, you can directly choose B because it is the only expression that includes a half. This is because it is an MCQ in order to save time. However, let me do it explicitly in this case. Now, minus can be distributed over this expression, and we would have half multiplied by k. We open bracket 1 over x1 square minus 1 over x2 square, which makes B to be the correct answer. A particle has a potential energy given by the position as function of the position x by u 9x squared minus 4x. What is the force on the particle at x is equal to a? So we're talking about the potential, then the force is conservative, and it can be determined from the potential via the calculus approach, minus du by dx. Now, here as you can notice that this can be utilized as an operator, d by dx of 9x squared minus 4x, and that would be minus 18x plus 4. We're interested in determining the component of the force at a particular position given by a, then fx computed at x is equal to a is given by minus 18a plus 4, which makes a to be the correct answer. Exercise 8, the relationship between the magnitude of the restoring force F and the resultant displacement x from the equilibrium for a nonlinear spring is given by the equation F is kx squared. What is the potential energy of the spring when it has been compressed a distance x0? So always in such type of problems, whenever we have the choices and we're talking about deriving one expression from the other, either by integral or by derivative, you can either start from F and try to determine the potential, or start from the potential and try to determine F. Usually the approach in this case from the potential to the force is easier because we're talking about derivatives. However, let me do it in this case starting from the force going to the potential. So the potential energy delta U can be determined from negative of a conservative force, the integral, or let me say delta U is given by minus the work done by the conservative force, which can be expressed as an integral from initial position to a final position of F dot dx. Now here notice that they gave us the magnitude of the force, which is not the restoring force, so we might get the answer correct up to a negative sign. However, luckily all of them are positive. Now let's replace the force F by its function given by minus integral of kx squared dx. Now let me set the boundaries of the integral from the equilibrium, which is 0, to a displacement x. We're not sure if this is an elongation or compression, so let me take it to be, okay, sorry, they told us compressed by distance x0, so minus x0, and that would be k is a constant, it would be dragged out, and x squared would give us x cubed over 3 from minus x0 to 0, and that would be the change in the potential energy U final minus U initial. Now U initial would be 0 because we started from the equilibrium, then the final potential energy in the spring is given by that. And now we're gonna compute this expression at x0 and 0. We can ignore the 0 because it's explicitly depends on x, and that would be minus k x0 to the power of 3 divided by 3, and we don't forget the minus sign here. Minus would give us k x0 to the power 3 divided by 3, and the correct answer in this case would be E. However, you can directly guess the answer to be E and save time by just utilizing that this can be derived. If you promote x0 to be a variable, then that would be 1 over 3k x cubed, and if you derive it, that would be give you kx squared, which gives us the same expression of F, making E the correct choice. Now exercise 9, a satellite of mass 120 kg is in circular orbit at a height h is equal to r above the surface of Earth. So basically this is Earth, and this is the satellite. It is orbiting the Earth at a radius, at a height, which is the radius. Then basically this is the radius of Earth, and the satellite have been placed at an orbit equal to the radius. Then the distance between the center of mass of the Earth and the satellite is given by the double of the radius of Earth. The radius and the mass of Earth are given by that respectively. The gravitational potential energy of the satellite Earth system is most nearly, here we're talking about the potential energy gravitational. not near the surface of a planet, but for a general case where it is given by the negative of the fraction gmm divided by r, where g is the gravitational constant and is given by 6.67 times 10 to the power minus 11 SI, and usually this constant is provided in the equation sheet. Now the radius, remember that the radius in this case, or r, is the center of mass separation distance, which is the double of r, and that would be 2 times 6.4 times 10 to the power 6. And in the numerator we would place the value of g, which is given by 6.67 times 10 to the power minus 11, multiplied by the mass of the first object, which is the satellite 120, multiplied by the mass of Earth, which is 6 times 10 to the power 24. Plugging this complicated expression on the calculator, we would have a value of minus 3.75 times 10 to the power 9 joules. And here notice that B and C are of same magnitude up to a minus sign, which means that we should use the potential energy gravitational exceeded with a minus sign or preceded with a minus sign. Then B is the correct answer. Now exercise figure 1 shows a block oscillating on a spring. The block is to the right of its equilibrium position, x is 0 and moving to the right. The two vectors indicate the spring force Fs and the frictional force acting on the block at the point. Figure 2 shows the block after it has reached its maximum displacement and returned to the same point. Which of the following indicates features in the figures that support claims as to where the spring force and friction are conservative forces? So remember that a conservative force, independent of the direction of motion, would always point to a direction toward the least potential. And if we're talking about a spring oscillator system, the force would always point toward the equilibrium position. However, other forces, like non-conservative forces like friction, would have a direction that depends on the state of motion. So if you're moving to the right, friction will be to the left. If you're moving to the left, friction would be to the right. A, since the magnitude of both forces is the same in both figures, they are both conservative forces. This can be directly eliminated because we know that friction is not conservative. Since the magnitude of both forces, they are both non-conservative, no, we know that the force of the spring is conservative. Since the spring force always point toward equilibrium and the frictional forces always point against the motion, they are both conservative. Although the first part of the statement is correct, but the reasoning is wrong, so we can eliminate this. Since the spring force always points toward the equilibrium and frictional forces always points against the motion, the spring force is a non-conservative and the frictional force is a conservative. This is wrong because the reasoning is wrong. However, the first part of the statement is correct. Since the spring force always points toward the equilibrium and frictional forces always points against the motion, the spring force is a conservative and the friction is a non-conservative, then E is correct. Now finally, exercise 11 as an exit ticket for today's class. When an object is moved from point A to rest at point B in a gravitational field, the net work done by the field depends on the mass of the object and the positions of A and B only, the path taken between A and B only, the positions of A and B and the path taken between them. Okay, we know that the gravitational field is a conservative force, and whenever we're talking about the work done by the conservative force is given by negative the change in the potential energy, and whenever we're talking about the change of the potential energy, this is U final minus U initial. This depends on the final position, this depends on the initial position, independent of the path taken, and in particular points A and B, which makes A to be the correct answer. And that's it for me in this video, guys. See you soon in a new one.